Let's look at finding the equation of a circle. And if we look over here, I've drawn a couple of circles to start with. One of them, the circle, the centre of the circle is at the origin O. And then this one here, we've moved the circle away from the origin. Notice that I've kept the circle in the positive quadrant for x and y. It doesn't affect the working, and it's a little bit easier to demonstrate when you're showing this. But the circle can be anywhere. Okay, let's start with our circle that's got the centre at the origin. When you find the equation of anything, you're trying to find a formula that connects x and y for any point, often called P, that lies on the shape that you're talking about. So P is on this circle. I want to know what is the connection between x and y, the x and y coordinates of this point P, if it stays on the circle. It's not allowed to move away from the circle. Well, I have here a nice triangle, and certainly on that triangle, Pn is the y coordinate of the point P, so Pn is actually y, and O to n is the x coordinate of P, so On is equal to x. So Pythagoras' theorem tells me that in this right-angled triangle that OP squared is always equal to the sum of the squares of the other two sides. So that's ON and NP. So that's a basic statement of Pythagoras' theorem, and we've used that already in some of our other coordinate geometry work. In this case, OP squared, OP is the radius of the circle. And you'll notice that as the circle goes round, the x coordinate here must be plus r because the radius is r, and across the other side the radius must be minus r. Sorry, the x coordinate must be minus r at that point. So OP then is r. So r squared equals ON is now x, so that's x squared, and NP is y. So we end up with r squared equals x squared plus y squared. Now we normally write that the other way round. So we normally write that x plus y squared equals r squared. And this is the equation of the circle. It's a formula with x and y in it that's always true. So that's the basic equation of a circle where the centre is at the origin. So if I write down something like x squared plus y squared equals, let's go for 12. What am I saying that actually represents? Well, it's in the right form. R squared is equal to 12. So r is the square root of 12. So this represents a circle, centre O, radius, the square root of 12. Now let's move on to the second diagram down here. In this diagram, the centre has been moved. The whole circle has been moved as a result. But I can still draw a right-angled triangle there. Now let's look at the distances involved here. We'll call that n again, I think. This doesn't hurt. So Pn this time is the difference in the y coordinates. So it's y take away k, where I'm calling the centre of the circle the point HK. And Cn, I've got a lot of space here, so let's Pop a little arrow in here to show that I'm talking about Cn. Cn is the horizontal distance along here, which is x moves from h to x, so the distance is x minus h. So Pythagoras' theorem this time tells me that PC, I can't use O for this point, of course, because I'm still using O for the origin. So C's a pretty good letter for centre, so we'll call that PC. So PC squared will equal Pn squared plus Cn squared. And there's no reason why I can't use R for the radius as well. So again, let's turn this round the other way in the same way as we did up here. Pn is, well, let's put Cn first because normally we would do that. So Cn is x minus h, so x minus h squared plus Pn is y minus k squared equals r squared. Okay, so I've transferred this formula to the top of the board to give me some more space. Now let's have a look at using that formula then. So if we wanted to find the equation of a circle, e.g., suppose we wanted to find a circle and the centre was at the point 4, -3, and the radius was equal to 6, we can use that formula straight away. It's not a difficult formula to remember because it's a bit like Pythagoras, isn't it? So we shouldn't have too many problems here. So h then is 4, so it's x take away 4 squared, add k, which is -3, be careful with your sign, so y take away -3 is y plus 3 squared. The radius is 6 squared. And that is, in fact, the equation, but usually they'll say simplify it or expand it out in some way. So we would expand out the bracket, so we have x squared plus 16, twice the product is take 8x, and then y squared plus 9, twice the product here, 6y, and 6 squared is 36. And then the conventional way of simplifying this is to put everything on one side, to start with x squared, and then follow it with y squared. Then we have usually the x term, then we have the y term, and finally we put all the numbers together. 16 and 9 is 25. Take away 36 is minus 11. And that's the equation written out in a simplified way. Now, sometimes you might be asked to do this in reverse. So they may give you the equation like this and ask you for the centre and the radius of the circle. So let's go for an example. Let's have x squared plus y squared plus 4x minus 6y minus 12 equals 0. There are tricks for doing this, which I'll show you at the end, which you may want to use. Tricks are always nice when you're trying to save time, but we should understand what we're trying to do. Now, the crucial thing is to visualize the x part and the y part separately. And we do a sort of completing the square on this. So x squared plus 4x is x plus 2 all squared. Remember the completing the square technique? You halve this number and then you square it and take it away again. So that gives us 4. And then the y part, halve that number, -3, square it and take it away again. And then finally take 12. Now, with one eye on our version up here, we can see that this will end up looking like this, because if I write that as x plus 2 squared plus y minus 3 squared equals, now we'll put the numbers on the other side, 4 and 9 is 13, 25 becomes plus 25. And that's it, that's good, isn't it? Because looking up, compare the two then, h is -2, k is 3. So the centre is -2, 3, and 25, the radius squared, so the radius is 5. So there, from this version, we've done the reverse process and we've got the centre and the radius. Not too difficult, is it? But if you want to save yourself even more time, there's a nice little thing that we could do here, because if you look at this equation here, look at the x part. If you halve that number and change the sign, then straight away you get that. If you halve that number and change the sign, straight away you get that. So the centre comes out of this pretty quickly. And how would you get the radius? Well, the radius, I don't really want to write this down too exactly, because I'd like you to try and learn it in words as a process. The radius will be the square root of square this number, square that number, so that's h squared and k squared, and then you take away that. And if I call that c, which it usually is denoted by c, in this case I'd be taking away -12, so I'd be adding 12. So I'd square that, which is 4, square that, which is 9, add those together gives me 13, take away -12 is plus 12, 25, square root of 25 would be the radius. Useful, but a little harder to remember, so perhaps it's safer to stick with this process here. Okay, so there you have then probably the best ways of handling the equation of a circle that you're likely to get.